So, we will follow from where we stopped actually. So, this particular corresponding to this option, they will be it will be repeating 32% of the time. So, this is how you can get, it is actually a question of roulette wheel selection, because as if you have got this pie diagram, this is 38%, 5% etc., for that simple algebraic problem that I took. So, as if you are rotating, and more probable that it will actually, the wheel will stop here, right. Wheel is rotated, and obviously less number of time it will stop here or stop there or stop there and so on. So, this is how it is done. So, weakest individual has smallest share of the roulette wheel and fittest individual. So, there are other ways of doing it, there are other ways of doing this also, there are advanced ways of doing it also, but my purpose here is to tell you that this type of algorithm is best suited for energy efficient building design or energy efficiency in building, where you have discrete variable and qualitative variable, because you are operating on coded variables. So, basically roulette wheel selection is fitness proportionate selection. Every individual is allocated a selection in the roulette wheel, of course. Sections are of different size proportional to individual's fitness, that is what it is. The fittest candidate has got the biggest slice in the roulette wheel, and the weakest candidate has the smallest slice. The wheel is then spun and individual associated with the winning is selected. So, that is basically generating random numbers. Wheel is spun as many times as is necessary. So, you had original population 40, say after I mean basic, if you check their fitness, then after that when you want to skip them. So, this is what you will be doing, right. So, this is how it goes about. So, example problem was there very much. So, this is how we do it. So, probability of being selection is given by fxi divided by sigma fxi, right. So, then we do what we call crossover. From two parent population I want to generate a new generation. So, what is done? You do the procedure called crossover. Crossover is nothing, supposing this is my chromosome. So, I take pairs, I take in pairs, and this is the one pair is a parent pair, and I generate new children out of those. Now, how do I do it? Basically, I will generate again a random number, and this time it would be random number of this many digits. I had how many digits yet? 3, 3, 6, 3, 9, 3, 12 plus 4, 16 digits here. In this one, the chromosome string is 16 digits. So, I generate a random number, 2 digit random number, but divide by 1 by 16. For example, if I find it between 0, 6 up to 0 to 0, 6, then this is the point. If it is 7 to 12, this will be so basically 1 by 6, 0 to 16 and 16 to 32 etc., etc. So, I can divide by 16 to get 1 by 6 here, right. So, 1 by 6 etc. So, supposing I have found out it is somewhere between 18 to 24, the random number is, then this is the position which I have selected for crossover. So, what I do? I take this 3 strings of this one and this 7 strings of this was how many 10, right, 3, 3, 6, 3, 9, no 16, right, yeah 16. So, 16 minus 3, this 13. Now, I make a crossover, this goes here and this goes down here. So, this goes here. So, this one is 0, 0, 0, 0. If you look at this, the color is disturbing, this color is not the right one. So, I use a color, let us say is something like this color. So, this is the crossover location. So, 0, 0, 0 and rest all from here, and in this case 1, 1, 0 and rest all from there. So, I have generated new population from the fittest population itself. First I find out, first step is to find out the fitness and select them, generate the, from the first step is to have randomly your choice. Your choice might generate a random number and generate a population size of even population size, find out their fitness, and from that you generate your new 40 population. right. So, 40 times you generate random number which are fitted, that you will keep, and then do a crossover. Crossover means from the parents you will generate new children. Now, these are both are fitter, both are fit, both are relatively fit, because you have selected that fit 40 population or fit population. From there you are doing the crossover, which means that if currently the new orientation that I am likely to get, the shape I am likely to get, they are only from the fittest ones. So, new children you have got. So, out of 40 you will generate another fit, randomly you will generate 40 children, a new generation has come. So, there are 40 parents, from that you will generate 40 children, because you will do crossover. So, each pair of selected string produce new offspring string, and the two mating strings are cut at a point, the resulting pairs are swapped with one another to form the two new strings. So, this new string now you evaluate again, right. So, parents, so then once in a while this might actually lead to what is called local optima. Sometime you might get stuck local minima or something like that, and leaving the global one, bigger one, local, supposing something like values are, fitness values are coming something like, fitness values are coming something like this, fitness values are, fitness are something like this, you will obviously maximize the fitness. So, it is all fit for only maximization, as you can see, and sometime you might find it varies with the variable, let us say decision variable like this, you are trying to maximize it, it varies, there is a small maxima, then there is a global maxima is much higher, you might get stuck here, because you will be operating around those population. So, what is done? Sometime you do what is called mutation. So, mutation, in mutation what you do, randomly you change, again generate random number, and randomly you change at one location, change 0 to 1 or 1 to 0, because you have only two cases. Supposing the population, so for example this was green, this was green, now here you suddenly change it to the, if it was green standing for this particular one, I mean this was 0 is blank is 0, red one is 1. So, this was actually, this was, let us say was this was in the new population, everything will remain same, but this was red, now it becomes blank, that means 1 to you have changed. So, randomly you change 1 to 0, so that it can come out from. Now, these probabilities are very less, you do not do it every time, you do it in once in a while, So, you do the mutation, so randomly change the binary digit from 0 to 1 and vice versa to avoid local minima. But this is not done every time, it is done once in a while, and probability of such thing is also fixed. You already decide, possibly 1 in 1000 times you will do this or something of that kind. It is needed because even reproduction and crossover effectively such and recombine the produced better and better population. Occasionally they may lose some potentially useful genetic material. So, this is this is actually a kind of mimicking the natural evolution process, So, sometime you may have. So, basically the GA cycle would be what then? To start with, you have a population, right, from there you are selecting, keeping the bests and then reproducing through crossover, mutation once in a while, look at this population, find out the best. So, this process continues till you do not improve upon the fitness value, Now, what will happen after some time, fitness value of all the members in the population are same. That means, there is no scope of improvement further, there is no scope of improvement further. Okay. So, in our case, of course, for example, if you take this example if you take, and now you go on doing this process, you will find that algebraically whatever is the fittest value of this one, you will arrive at that, and all all these members of the population will have the same fitness value, because you are combining and recombining, doing all sorts of things, crossover, same orientation will come, they will repeat, and finally all population will have the same values. So, that is the idea. So, this is what is done, and now here there is one problem, because it is always a maximization, and survival of the fittest principle is adopted. Therefore, the need for objective function. So, it fitness function maximizes. How do you minimize it? Because we have minimization function, minimize the cooling load, might maximize the thermal comfort, but minimize the cooling load. So, therefore, you can use function like 1 by Fx, where Fx is the cooling load, right, or one can use 1 by Fx to the power 3, various ones can be used. Fx is minimization of heating or cooling load, right, and if it is maximization of thermal comfort, then you do not, obviously you do not write maximization from deviation, maximization of deviations, maximization of thermal comfort, which it mean the deviations from the comfort zone is minimized. So, you can actually do it. So, objective function cannot be explicitly related to decision variable in our case, cannot be explicitly related. However, we can be calculated by step design procedure. So, as I said, frequency domain and time domain solution procedures are there, which I am not going to discuss here. I just told you that you can use GA together with such procedure to come out to the best solution. So, this is 8 possible orientation of a building for different possible. So, again aspect ratio one thing, roof 8, this 16 as I said, and this is 8 possible and 8 possible glazing. The examples are being shown here. Shape involves length, breadth and height of the building, which I showed earlier. They are formed according to the building bylaws. For example, you can take DDA master plan of Delhi, and ground cover is 31%, 32, 33%, aspect ratio 1, 1.52 and 2.4, floor area ratio you take fixed, this is fixed, plot size is fixed. So, you are actually getting 4 into 4, 16 cases, 30% ground coverage, aspect ratio of 4, 31% ground coverage, aspect ratio, all this. What is aspect ratio? L by L and B, this is B. So, this ratio is 1 is mean square, 1.5, longer dimension 1.5 times than the shorter dimension, and then 2 and 2.5 etcetera etcetera, and ground coverage. So, you can get 16 variables, that is how you get 16, right, and plot size is fixed, because that is there, and this is a constraint, this is also fixed, one can keep them constant. So, using this data 16 different possible shape of the building can be finalized. Height you can keep as fixed. If you vary, you can vary, the number of variables will increase only. So, fitness function something is like this one can use, and then one can write it in some program, you can write it in, but for the class purpose you do not have to really write the program, but one simple method is using admittance procedure, which I am not teaching you in this class. In building science class, of course, they are covered, and generate quick and more accurate thermal optimization model you can generate based on this. So, this is what I said, shape, and these are the roofing materials, 8 roofing materials. I showed these similar examples earlier. Their U values are like this, then various wall and their U values could be something like this, various glazing material they could be something like this, and number of generations. Okay, so population size has been taken 20 here, crossover probability is 0.6, probability of mutation 0.03, procedure is roulette wheel selection, single point crossover and uniform, you can also have double point crossover and all, here is single point crossover and uniform mutation. So, that would be the start, give the input building data, obviously the climatic data is needed for the building, then decision variables, then program, plant load calculation, GA operations, and the stopping criteria is when let us say 90% of the values are all same, fitness values are same, that could be stopping criteria, and that is the end of it. So, this is what it is. Supposing I take an example, plot area etcetera, which I just gave you, and you can take even building master plan into account in this one. right. So, for this kind of plot areas, if you have taken this, some of this maximum height and all those are prescribed, then objective function is minimized 2 times cooling load plus the heating load. You are minimizing, therefore, 2 times cooling load, right, maximizing, minimizing the heating load. Cooling load is taken twice the weightage is given because of the cost, and heating load is just once. That is what I said. And if you see that after number of generations, the fitness value, this is average fitness value. Average fitness value become constant, that means all of them have got same fitness value, right. So, this is the average fitness value, the blue one, and maximum value is here this much, then it is this much, then this. So, maximum and average they all become same when it, when after that you need not. So, therefore, you can actually doing an exercise initially, you say that after 35 iterations, 35 cycles, I will not do further. So, after 35 cycles, or depending upon your case, sometime it may be order of around 50 cycles, which when it will tell you that it has reached this optimization, right. So, this is for a given climate, let us say in composite climate, something of the Delhi kind, and this is something of the kind of Jodhpur hot dry desert, right. So, after some period you find that all becomes same. Warm humid climate, something like Chennai, Mumbai, Kolkata or similar. So, there you can find something of this kind, and you find that this is your finally optimum solution 1 for such kind of situation. So, you know the orientation for each climatic situation you can get, right, you can get the best solution, you can get the best solution using such kind of optimization process. And optimal solution 2, that is the next to the best, if you look at it, that also you can look into, and next third best also you can look into, right. For L shape, for what shape of the building was considered to be rectangle one and another L shaped. So, separately for L shaped building with different aspect ratios, and L shaped building and optimized building with conventionally designed building, then one can compare by using software or I mean using the same basically. You can calculate out the cooling load, you will find that you will get much better cooling load for conventionally designed as practiced. It would give you something of the kind of, let us say, kilowatt hour 1680 to 81, in this case it is nearly half, right. This is the third best solution, even that is nearly half of this, this third best, etc., etc. So, you can look at heating load is this much, heating load here was 1000, here was 5000. So, you can see that best, even second best or third best solutions are much better than just using arbitrary solutions, and L shaped building also similar sort of thing one can see. And if you use a software to see the value, for example, TRNSYS is one of the software. So, if you this not require snapshot, unless you know TRNSYS you won't know. So, you will find that this is solution 1, this is from TRNSYS and this is from GA model using a procedure of calculation which is much amenable to hand calculation. Relative results are more or less same. This was the best, well this is near best, So, if you are selecting between these 3, this also says that this is best. If you compare the conventional, you will find the difference, the best, the best if you calculate them out. So, they are something like this. For example, these 3 are from the best 3 for optimization, and they give similar result based on the software also, any software. So, basically since I am selecting relatively best one, a very sophisticated robust software may not be needed, relative results will still be same to start with design. You might verify this for, but if you are interested in calculating or estimating annual energy load, then you have to use the software to verify the same, right. So, that is what it is L-shaped building also it will show you similar. This is from admittance procedure, optimal ones, and this from the software, this from similarly from and this again from the software and this one, right. So, in all cases it would give you much better than a conventional design building. So, this is fine, but I think I will just tell you about non-air conditioned building at the last part of it. Now, non-air conditioned building, cooling load we do not calculate. We calculate what is called some sort of comfort indices. Now, there are various comfort indices. One which is simple and suitable for country like India, tropical countries, is called tropical summer index. These are actually developed by selecting individuals, healthy individuals between the age group of 20 to 60, putting them into the given environment and asking their subjective response. There are other ones, there are improved ones also, there are modern ones, some of the softwares also can give you some idea. So, what, but then this is a classical one and it has got, it is simple algebraic. So, it is pretty useful in that sense. Now, what are the factors which governs your thermal comfort? Number one, it is a temperature. Number two, relative humidity. Number three, air velocity, fan, etc. Number four, radiation from surfaces. What I mean to say is, the temperature inside the room, if it is high, you start feeling uncomfortable. So, there is an temperature is one aspect, but even the temperature is low, relative humidity is high, you start feeling discomfort. Why? Because body can cool itself by evaporative cooling. From the skin, sweat can evaporate and cooling occurs. In still air, this cooling will depend on only on the relative humidity. If the relative humidity is high, this cooling will not occur, right. Evaporation cannot take place, but supposing I have a fan, then that will remove some of the heat from my skin. If the surfaces are very hot, they would also radiate heat into my body. So, temperature, relative humidity, air velocity, local air velocity from fan or something of that kind. If it is naturally ventilated, even if you can design for natural ventilation, air coming from outside, if it is cool air, then that can actually remove some heat from your body, and radiation from the surfaces. So, all these are combined in tropical summer index, or for that matter any thermal comfort index, right, any thermal comfort index. So, we would like to, so this is given by this formula. Tropical summer index is given by this formula. dBT stands for dry bulb temperature, temperature inside the space. V stands for air velocity. WBT is called wet bulb temperature, that is actually related to relative humidity. Difference between dBT and WBT gives me relative humidity. Okay, just let me now explain how what it is actually. Let me just explain what is because you may not, some of you may not have been exposed to psychrometric chart or similar sort of thing. Or now what we do is, when we want to find out relative humidity, this is, if I have a thermometer, mercury thermometer, if I measure the temperature, that I call it dBT, dry bulb temperature. Now, supposing same thermometer, now this bulb is kept wet by putting wet jute. Evaporation will occur from here, So, the height, this height and height here would be less. This difference, there will be a difference in this height. This is called wet bulb thermometer temperature, wet bulb temperature, and WBT will be less than dBT. WBT will be less than dBT, except for the case where it is relative humidity is 100%, where no evaporation can take place from here, and therefore, relative humidity is 100. So, relative humidity is a function of dBT minus WBT. This we call as wet bulb depression. This we call as wet bulb depression. So, so therefore, in this model, as you have seen, WBT is directly taken, which is a measure together with the dBT is a measure of relative humidity. It is a measure of relative humidity, right. So, this is the formula. Now, this easily you can calculate out. Now, this the range of comfort range for this one is also given 25 to 30. This is all expressed in degree centigrade. This is an empirical equation. So, simple way is to, if you know the air velocity and inside the room there may not be any air velocity, you might assume to be 0 or whatever it is if there is no air velocity. So, you can find out, and if it is within 25 to 30 is comfortable. So, what we can do is we can actually find out the deviation from this. So, lower limit of this is 25, tropical summer index lower limit is 25 and upper limit is 30. So, the value which is there at a given time, lower limit minus this TSL lower and TSL upper which is 35, 30, this is negative. I would like to, so this two both will be negative. Actually, lower limit is less than the room temperature, upper limit is also less than the temperature, this will be negative. This one I can, so the deviation from this I can actually maximize, minimize, sorry, deviation from or negative deviation I can maximize. So, these are negative values, as you can see, these are negative values and I can maximize. Now, how do I find out this T? This has to be again calculated through the admittance procedure or some such procedure. The inside room temperature every hour has to be calculated knowing the outside condition and all using the same procedure that I talked about, right. So, once you know this, deviation from this one can minimize, or if you are to maximize negative deviation from this one you can maximize, or you can use a fitness function like this 1 over this deviation, simply absolute value of this deviation 1 over this deviation, and this is summed up for 24 hours. This is summed up for 24 hours and this is maximized fitness function, because minimization of a negative function is equivalent to maximization, negative value is maximization. So, this is what we do. So, Fy is this, sometime one may use a power and so on and so forth, and therefore, you can find out which is better. So, rest all remains same, average deviation you can find out, number of hours, etc., and you can find out the best selection, total total even weighted, you can use some weighted function. For example, deviation is 28 for 52 hours, for 1.6 is the deviation for 36 hours and so on. So, you can actually find it out this deviation, and you can select the best one which gives you the best value based on least deviation in a way, based on least deviation. So, therefore, same procedure follows for all kind of buildings that there, and you can find out then optimized building and conventional building. So, conventional building for month of January it shows beyond tolerable lower limit, sometime it is above this, So, this is conventional is optimized building, sometime it could be lower depending upon composite monsoon climate. So, this is what it is, upper limit this will be cooling it, comfort limit. So, and this was not during it was not comfortable for a given type of building. Month of June, for each month one can look into this upper limit. So, most of the time this is below lower limit, this is above. So, one can find it out in this manner, and upper limit lower limit this is also here, this is. So, it has a tendency, if you use 2, that factor 2 times, depending upon the type of objective function you are using, if you use a weightage function for the summer heating, and like you think that summer cooling is summer higher, summer discomfort is more important than winter discomfort, then you can put a weightage factor, or appropriately one can do. So, this procedure can be used to actually find out both for condition and unconditioned. And if you are using financial evaluation, then you can calculate out the energy load and cost of the energy and so on. Operational cost that we talked about in the beginning, operational energy. So, economical, so you can use something like this. So, initial cost of the envelope, operational cost you can look into, and energy cost, and then put the present worth with some interest rate, and you can check, and that is what would it would show that even cost wise, life cycle cost wise, optimized one will have much less life cycle cost. Considering operational energy and energy cost, it will be much less. So, this is what it is for L shaped building. For conventional and optimized, there will be saving in energy, and that is it. So, I think with that this is an optimization process which you can adopt for minimizing your operational energy, which is important. Although the procedure for calculating the energy load I have not discussed, but the optimization process that can be used for such a situation where your variables are qualitative and discrete, that is what I am.